A tinsmith wishes to make an open box from a square piece of tin which measures 8 inches by 8 inches. To accomplish this task, he proposes to cut equal square pieces from each corner of the tin and fold up the tin to form sides. Determine the sides of the squares to be cut from the corners so that the box will have the greatest possible volume, and what is the volume. So we'll set up a picture. So we're cutting out the corners. I'm going to let each of the sides of each of these corners be represented by x, which means that a side of the whole piece of tin would be represented by 8 minus 2x. Our sides of our square that we're going to cut out must be between 0 and 4, because if we cut more than 4, then we've taken up the whole side of the box. We're trying to maximize volume. So our volume would be length times width times height, which would be 8 minus 2x times 8 minus 2x times x. Multiply that out, we get 64x minus 32x squared plus 4x cubed. Take the derivative of that, so that's equal to 64 minus 64x plus 12x squared. Set that equal to 0. I'm going to divide everything by 4, and that would reduce this to 3x squared minus 16x plus 16. If we factor, we would get 0 equals 3x minus 4 times x minus 4. And we'll set each one equal to 0, and we get x equals 4/3 for this one, and x equals 4 for this one. But as we said, we can't use 4 because that would cut off the whole side of the box. So that eliminates 4 as a solution, so we're only dealing with x equals 4/3. We'll show that the derivative is increasing to the left and decreasing to the right, which if you plug in a value to the left of 4/3, you get this to be positive, and you plug in a value to the right of 4/3, you get this to be negative. So that's a max at x equals 4/3 since v prime changes from plus to minus. So the sides of our square should be 4/3 inches to maximize the volume at approximately 37.926 inches cubed, and you can get this by plugging in 4/3 into your volume function.